Good morning. I take this opportunity to thank the organizers for giving me a chance to present my work in this conference. I shall be speaking about compact objects in a wide variety of categories. Compact topological spaces were first characterized by Kuratowski and his student Stanislaw Mrówka, which came to be known as the Kuratowski-Mrówka theorem, which states that a topological space is compact if and only if every filter on X clusters in this sense, and for any other topological space Y, the second projection of X cross Y to Y is a closed map. Spaces have been investigated in categories for a long time, either by categorical closure operators, for instance by Dikranian, Tholen, Giuli, Tosi, Clementino, to mention a few, or by categorical interior operators by Worcester, Castellani and his students, David Holgate, Razafindra Kato, Schlapal, again for some. By axiomatization of closed morphisms by Clementino, Giuli and Tholen in around 2004, axiomatization of proper morphisms by Dirk Hoffman and Tholen around 2010. So there exists an extensive literature around this. In this present work, we shall be trying to internalize the notion of a neighborhood in a wide variety of categories. For instance, in all small complete and small co-complete categories which are well powered. It seems that this approach is much more general than the categorical closure operators. The first notion that needs to be told in this approach is identifying a triplet consisting of a category and two sets of morphisms, where the category A is finitely complete, it is finite coproducts, it is proper factorization structure, and for each object, the M subobjects of an object make a complete lattice. The contexts are everywhere. Sets, topological spaces, measurable spaces, every kind of universal algebras, locales. And these are all examples of the more general case of a small complete, small co-complete, well-powered category. Another stray example is of finite sets and surjections. A third kind of examples come from schemes or opposites of Zariski categories, where Zariski categories were studied by Diers and they turned out to be models for commutative algebra. If one has a context, then for any object, the category of bundles over that object is also another candidate for a context. Thus, contexts are everywhere. We will need the notion of a filter on an object, which is none else than a filter in the lattice of admissible subobjects, and they are defined identically. The set of filters make a complete algebraic lattice, with compact elements being up X as shown over here. The word compact is used in the usual sense of lattice theory. Filters of X is distributive if and only if the subobject lattice is distributive. We are now ready to introduce our pre-neighborhoods. Recall in the classical case, in describing a topology, each element of the set, each point is assigned a neighborhood. We do the same over here, but we do not have points, we only have subobjects. So every subobject is assigned a filter, with the condition that if a subobject P belongs to the filter at X, then P must be bigger than X. And as X gets bigger and bigger, the filter at X gets smaller and smaller. So this describes a pre-neighborhood system. And obviously the pair X mu will be called an internal pre-neighborhood space. Now, when a pre-neighborhood system is interpolative in the sense that for a pre-neighborhood P of an object X, there exists another pre-neighborhood of Q of X such that P is already a pre-neighborhood of Q. So, in this sense, it is interpolated. It is called a weak neighborhood system. And furthermore, the demand that each pre-neighborhood of a join is actually the pre-neighborhood of each of its joins gives us internal neighborhoods. The moment we have different neighborhood systems, we can discuss what are its morphisms. And that is done as usual, given pre-neighborhood systems mu and phi on x and y. A morphism f from x to y is a pre-neighborhood morphism if every pre-neighborhood of a subobject of the codomain, the pre-image of the pre-neighborhood under that f is a pre-neighborhood of the pre-image. So this is just as we do in topological spaces. For neighborhoods, we have to be a little more careful. We have to restrict ourselves to morphisms which preserve arbitrary joins. Now, this condition is not of concern in sets because the image pre-image adjunction, the pre-image has a further right adjoint, and hence this is automatic. However, in general contexts, that may not be the case. This gives rise to the categories of neighborhood systems, and then we are ready for our first result, which says that the pre-neighborhoods are much more general. So, for each object X, let Gx be the complete lattice of grounded monotone extensional endomaps on the subobjects. Grounded means the endomaps preserve the smallest subobjects. Complete lattice, the lattice is coming from pointwise order. Pre-neighborhoods are already filtered, so they are compared by comparisons as subsets. So they also make a complete lattice, and there are two very natural maps in the reverse direction as shown. It turns out that the map phi is a left adjoint of the map psi and is a right inverse of psi. So Gx is actually sitting inside pre-neighborhoods of X, inside the dual lattice of the pre-neighborhoods on X in a co-reflective way. In case of finite sets, this map phi is an isomorphism. But the presence of discrete Hausdorff spaces show that in case of sets, it is not an isomorphism, and it's in general an embedding. So we can see that grounded monotone extensional endomaps are dually co-reflectively inside pre-neighborhoods, and hence in this sense we can think of pre-neighborhoods being much more general than closure operators, which are also special cases of grounded monotone extensional endomaps. The categories of pre-neighborhoods and weak neighborhoods are topological. So this tells us that we can bring in the analogy of weak topologies and weak and strong topologies over here. That means, in other words, given a limiting object, we can create the smallest pre-neighborhood system on the limiting object such that each component of the limiting cone becomes a pre-neighborhood morphism. Dually, on the co-limiting objects, we can create the largest pre-neighborhood system which makes each of the components of the co-limiting cone pre-neighborhood morphisms. For neighborhoods, we have to be much more careful. Provided every morphism preserves joins, then neighborhood is topological. So we are now ready to define the closure of a subobject in an internal pre-neighborhood space. As usual, the closure should be the join of all those subobjects whose every neighborhood intersect P. But we have to be careful that we do not select the largest subobject, which is the identity, because for that this condition is trivial. So we select all the proper subobjects of X whose neighborhoods intersects P and take the adjoint, and that's the closure. Once we define the closure, we can define what is mu closed, the set of all mu closed things, and closed morphisms are then morphisms which preserve this closeness. That is, P is closed in the domain implies its image is closed in the codomain. And ACL is the set of all closed morphisms. The closure hereby defined turns out to be a proper closure operator, a valid closure operator in the sense it is monotone, idempotent, extensional, and grounded as shown. However, this is something new. We don't see this in case of sets in topological spaces, because when mu and phi are topological spaces, it is automatically continuous with respect to the closure for mu and the closure for phi. But here, the pre-neighborhood morphism needs to satisfy an extra condition to become continuous. Now, what is this condition? The reflecting zero condition is very natural. A morphism reflects zero if the pre-image of the smallest subobject is the smallest subobject. It can be shown that a morphism reflects zero if and only if whenever the image of a subobject is trivial, the subobject is automatically trivial. Or whenever a subobject of the codomain fails to meet an image of a subobject, then the subobject fails to meet the pre-image of that. Now, if every morphism reflects zero, the initial object must be strict. On the other hand, in presence of the property that the unique morphism from the initial to the terminal is an admissible monomorphism, strictness of the initial object ensures that every morphism reflects zero. Now, this special condition needs some reference. Bourne, Goswami and Yanowitz in two occasions called such categories where the unique morphism from the initial to the terminal is a monomorphism as quasi-pointed. Now we require that this unique morphism is not only a monomorphism but an admissible monomorphism, and such contexts we shall call admissibly quasi-pointed. Several contexts like sets, topological spaces, measurable spaces, locales, they are admissibly quasi-pointed simply because this unique map turns out to be a regular monomorphism. On the other hand, rings with identity and homomorphisms preserving this identity is not even quasi-pointed. But their opposite category, or the opposite category of Zariski's categories, are quasi-pointed. So it turns out in admissibly quasi-pointed contexts, initial object is strict if and only if every morphism reflects zero. So, reflection of zero is a property innate to the category, and this has to be either put on the category to tame it and make every pre-neighborhood morphism continuous, or the continuity has to be put inside the definition, which is usually done in approaches in categorical closure operators. Additivity is also a question over here. If because of the presence of prime filters, our subobject lattice is just a complete lattice. And for non-distributive lattices, prime filters are very rare. Even maximal filter need not be prime. There's a beautiful paper by Marcel Erny who investigated this. However, the closure operator is hereditary. That means a closed subobject of a closed subobject is a closed subobject. When we have a closed morphism which is stable under pullbacks, so it means that X, we have a pre-neighborhood morphism and another pre-neighborhood morphism G. Whenever we take the pullback, this pullback is closed. But Z had a pre-neighborhood system. The topologicity ensures that there exists a smallest pre-neighborhood system on this pullback, which makes these pullback projections pre-neighborhood morphisms. And that is this. So that is the full definition, that with this with this weak pre-neighborhood system, Fg becomes a closed morphism. Examples in familiar cases are the same old ones, precisely the same old one. In locales, something needs to be stated. Themba and Igedo investigated what is now called a T-neighborhood system. So for a locale X and a sublocale S, its T-neighborhoods are all the sublocales such that between S and T there is an open sublocale. This turns out to be a neighborhood system on X. And the functor, which assigns to each locale this X with this T neighborhood system on X, turns out to be a right inverse to the forgetful functor, which means that this T neighborhood system is a canonical neighborhood system on locales such that each localic map becomes a pre-neighborhood morphism. And hence, the theory of locales turned out to be a special case of this present theory. And we have proper maps to agree with the usual proper maps of locales when they are put these T neighborhood systems. Here is an alternative way of looking into proper morphisms. Pre-neighborhood morphism is proper if and only if for all other pre-neighborhood spaces Z, the product with the identity of F is closed. Not only that, for every subobject of Y cross Z, the pullback of this product along that subobject is also closed. Here are some properties of closed morphisms and proper morphisms. The first row says how big they are. The second one is about their closedness under compositions. The third row is about cancelability properties. And the fourth one is about stability under pullbacks. The things in yellow are ones where firstly continuity is required, and secondly a few other conditions are required. For instance, formal surjection. Well, a morphism is formally surjective if it satisfies exactly what we know in usual set theory as being surjective. So every subobject of the codomain is an image of some subobject there, which is equivalent to saying the co-restriction of F along every subobject of the codomain is in E, is a good epimorphism. Also, there is this continuously stably in E. It is just simply meaning that F is continuous, it is in E, and every pullback of it is continuous and in E. So, this table actually gives us a very good way to judge how continuity enters into our consideration and where it is not required. We are now ready to speak about compact things. This is the smallest pre-neighborhood system, this is the largest, and since the terminal object is the empty product, we must always assign it the smallest pre-neighborhood system. Well, now, an internal pre-neighborhood space is compact if the unique morphism is proper. and Ka is the subcategory of compact pre-neighborhood spaces. By definition, every isomorphism is proper, so the terminal object is always proper. Now this one is same as the discrete in the case of sets, but for instance in the case of schemes this is not. So one has to be careful in executing this definition. The alternative characterization of proper maps immediately give us the third condition of Kuratowski-Mrówka in this case. So it's compact if and only if for all pre-neighborhood spaces the second projection is a closed morphism. The others are quite similar. This one is very similar to the classical case. Over here the surjection is replaced by stably in E condition. So such images are this, and category of compact is finitely productive and closed Hereditan. Here we just rewrite the same notions what we have for sets, but now for sets of subobjects. So what does it mean to have a finite intersection property? So it is something very similar. So, but I rewrote it for clarity. So the first criterion, filters imply compactness. So in a reflecting zero context in which finite product projections are in E, the clustering of filters imply compactness. For the converse, we need a little better kind of categories. A category in which finite sums distribute over pullbacks is called extensive. It was studied by Carboni, Lack, and Walters. The extensive means a finitely complete and extensive category. So these are categories where sums are well behaved. In an extensive context, the initial object is straight. The coproduct injections are admissible monomorphisms, and hence the unique morphism is an admissible monomorphism. So such a place we have an admissibly quasi-pointed context. Every morphism reflects zero. Every pre-neighborhood morphism is continuous. So an extensive context is a special case of a and the second condition remains the same. The finite product projections are good epimorphisms. Then compactness implies that every filter is cluster. Recall that a lattice is pseudo-complemented if every element has a pseudo-complement, which is the largest element which is disjoint from that. And we called a subobject in a pre-neighborhood space with system mu to be mu open, provided P is its own neighborhood. And the interior with respect to mu would be the join of all the open things below P. The assignment of P going to interior of P is monotone, idempotent. Intentional means it is smaller than P. Fixing every mu open sets, the smallest subobject is mu open, it's closed under finite intersections. But the closure under arbitrary joins holds if and only if the interior is also open, mu open. And if this happens, we have these two formulas. So, however, what is more important for us at this present moment is that neighborhood systems all satisfy this property. If you have a pre-neighborhood space with mu interiors open and subobjects pseudo-complemented, pseudo-complementation produces an adjunction between the closed and the opens, which are both complete neat semilattices. And hence, this adjunction induces an isomorphism between star closed subobjects and star open subobjects. So therefore, if you have a filter of star closed subobjects, which has non-empty intersection, then if every filter of star closed subobjects have non-empty intersection, is equivalent to saying every star open cover has a finite subcover. This is immediate from this isomorphism. And that gives us the Krotowski-Mrówka theorem in this context, wherein in every extensive context in which finite product projections are in E, X mu is a pre-neighborhood space with mu interiors, mu open, and subobjects is pseudo-complemented. Then the usual Krotowski-Mrówka theorem holds, with open cover being replaced by star open cover. I'll stop here. I cannot produce the proofs because of lack of time, but the proofs did really show some novelties of this approach on one hand. And on the other hand, before ending, I want to make a note that internalizing this notion actually tells us which properties depend on innate properties of the category where it is internalized and which properties are independent of it. So we can exactly identify the consequences of a property. And I stop here. Thank you.